Welcome to Ask and Learn.
Okay, so for this problem, we're given that we have this kind of hemisphere shape, and we're told that there's an electric field going like this, and we're asked to find the flux through the flat surface and through the curved surface. And so let's start with the flat surface. Oh, and actually, let me write down my givens before I get any further. So this electric field is 2.5 newtons per coulomb. That's a beautiful 5. That's okay. It's not a critical part of the problem. And the radius is 0.0568 meters. 3 sig figs. Okay. And we're asked to find the flux through the flat surface. And so the electric field's uniform. So the integral of E dot dA is just going to be the electric field times the area, and the cross-sectional area is pi r squared. So when I plug that into a calculator, I got 0.025, and then notice that it's negative because we generally define the area vectors as going out. So E is in the opposite direction of the area vector. So the cross product, or excuse me, the dot product between the two is negative. And so let me just double check, minus 0.025. Newtons per coulomb meter squared. I think that needs a better unit. Okay, and then we want to get the flux to the curved surface, and we can use Gauss's law to say, well, look, if there's no charge enclosed, then the total net flux has to be 0, and so the flux through the outer surface has to balance, or excuse me, the flux through the curved surface has to balance the flux through the flat surface. And so you can say the phi through the curved surface, I guess I'll call this F for flat and C for curve, is 0.025 newtons per coulomb meter squared. And just a note on the signs, I mean, this is just based on the convention that the area vectors for shapes always point out. And so you can see that it kind of makes sense that this is positive because the area vector is points out as well. And so they're roughly in the same direction. Or at least A has a component that's along the same direction as A. How about that?